Hey everyone, today we're going to be looking at limits of piecewise functions. So, we have a piecewise function here and we're going to take the limit. Uh, I'll explain a little bit. So, piecewise functions, what are they? Well, they're functions that take on different slopes as you cross intervals. So for instance, in this one, for every value that's 3 or greater for our x, we would use this equation to define the slope, and for every value that's less than 3, we use this equation to define the slope. So, or rather, not necessarily slope, because these are all, well, not straight lines, so we would use it to derive a derivative, or differentiate to get a derivative. But these equations define the curves that happen on intervals for piecewise functions. Usually, see them in like school, they're like straight lines and stuff. Maybe not, I don't know, but they're usually not that crazy. So here we're gonna take the limit. So let's take the limit as x approaches 3, and this time we're gonna do it from the positive side. So that way we will have to use x cubed minus 27 over x minus 3. So let's write that down. And I should probably explain what a limit is. So a limit is essentially seeing what happens to our y values as x gets closer to some arbitrary value. Not necessarily equaling it, but as you get closer to it, you see what happens. And the reason we don't just say, oh, x should just flat out equal 3 is because in this case, we plug in 3 and we get 0, right? We get 0 over 0, which I guess in this case that's good, because now we can use L'Hopital's rule. So I'll do that here. Differentiate, so that gets us 3x squared. Differentiating a constant is just 0, and over 1. Now plug in 3 after using L'Hopital's rule, and we see that we get 27. And this is by LH for L'Hopital's rule. So, like I was saying, with limits, we don't just plug in the value, unless we want to use L'Hopital's rule, that is. But typically, we don't just we don't plug in the value when we take a limit because that's the point of a limit. We see what happens as we get closer. You can test out limits, obviously, by just plugging it in and seeing if you get an undefined answer. If we had like the limit as x approach 2 of 1 over x, yeah, you could just plug in 2 and say it's 1/2. But for many cases, they will not be that easy, and plugging in will not get you an answer. You'll have to do more work. So that's the idea of a limit, and beyond just approaching a value rather than flat out equaling it, because it's still undefined at that, we're just seeing what happens as we get close. We have to approach the same value from both sides. So I mean, I have this plus here for saying that we approach 3 from the positive side, meaning we start at a value larger than 3, and then we go down. Had it been 3 with a minus sign, it would have been we start at a value less than 3, and we work our way up. For a limit to exist, they have to approach the same value, whether you're going positive or negative side. And we're going to get into that with this next example. Oh, I'm not going to erase because I painted the whole thing black, so I don't want to get rid of that. Anyway, so for the next one, let's take the limit as x approaches 0 of x squared, and since it's approaching 0, we would have to use our this part of the piecewise function where it's less than 3. So x squared plus 5x minus 13 over x cubed. Now, like I said, we're only looking at what happens when we get close to that value. And because I didn't give a sign for this one, it's not 0 plus or 0 minus. We have to see what happens for both sides. So, what do we do? Well, we plug in 0. We get the whole thing divided by 0, which is not good. But we can break this down into 2 limits, actually. So we'll take this, change it into the limit as x approaches 0 plus of x squared plus 5x minus 13 over x cubed. And also limit, I'll write another arrow here, limit as x approaches 0, but this time from the negative side, so like going up towards 0, we would have same thing, x squared plus 5x minus 13 over x cubed. Now, what happens? Well, regardless, you plug in 0, you're still dividing by 0. We know that the top will just be negative 13, but that's not exactly helping us. Well, it sort of helps us. Essentially what we can do is, because the other terms in the numerator just go away when you multiply by 0, we can instead take this as just the limit as, well, 2 limits if you want. We'll do 2 this time. And because it's in the denominator, we would have 1 over x cubed multiplied by negative 13. We'd also have the limit as x approaches 0 on the negative side, well, the same thing, also multiplied by negative 13. Now what happens? Well, 1 over x is a pretty popular function. I think it's called a hyperbola, but I could be wrong. And if there's one thing everyone should know about hyperbolas, it's that they're just the graph of 1 over x. It's that the limit does not exist because, well, if you go here, let me use a calculator for this. Actually, I don't need a calculator. Okay, so if we had 1 over, let's start from 0, from the positive side. 1 over 1 is equal to 1. 1 over 0.1 is equal to 10. And 1 over 0.01 is equal to 100. So as you can see, as our denominator gets smaller, it's getting closer to 0. The outputs are getting larger, as in, that looks kind of like an infinity sign. Oh well. So the point is, as we get closer and closer to 0 from the positive side, our values explode to infinity. They diverge. So that's one part. Positive side, this seemingly goes to positive infinity, and then multiplied by, well, yeah, it seemingly goes to positive infinity. Right, this negative 13 doesn't really matter because, well, it's infinity, so doesn't matter a whole lot. You don't really do operations with infinity. It's just what it is. And likewise, or rather, I guess you could argue that times negative 13, we get negative infinity. But that does not spell good news for us, because if we approach 0 from the negative side, just add a negative sign to all these, we get negative 1, negative 10, negative 100. So it's evident that even though we're, getting closer to 0, just from the opposite direction this time, we now have our values exploding to negative infinity, which positive and negative infinity are like completely opposite of each other. They're quite literally infinitely apart. So this goes to negative infinity, and negative infinity times negative 13 gets us positive infinity if you want to do the operation. And obviously infinity does not equal negative infinity. Does not equal negative infinity. Therefore, we would say that, at least for this one, the limit does, oh man, this is going to take a little bit, does not exist, because our values just kind of diverge from each other. They don't approach the same value. And just to show that graphically, I have it here on Desmos. Obviously, as we get closer and closer to 0, as this limit is implying, well, our values explode up to positive, negative infinity, x equals 0. We can see that as it gets closer to 0, we have an asymptote, and the limit does not exist. So yeah, that's limits of a piecewise function. Nothing too crazy, just a little bit of L'Hopital's rule and intuition on what limits do. So yeah, thank you for watching.